Well, good afternoon. Thank you very much for joining me again. We're up to 8. I'm slightly later starting compared to normal, so sorry about that. But we've had 5 minutes or so to log in. So we'll start in the usual way. Our title today is Transformer Calculations. If I can advance the slide on, I don't seem to be able to. Bear with me one moment. There we go. Title Transformer Calculations. I'll give you the usual 3 minutes to do the usual jobs, and then we'll start with one of those quizzes. So once again, if you want a scrap piece of paper to hand, be my guest, that's absolutely fine. So, three minutes on the clock, and we'll make a proper start. Thank you. Thank you very much. That was 3 minutes, hopefully time to do those usual jobs. We'll start with one of those quizzes. You might have just seen me scribbling down. I had a look at the first answer I had printed off. Sorry, the first question I had printed off. Didn't like it. I've gone for what I hope is a more interesting one. So here, coming up now, are 5 questions about anything from the past 2 years of physics. And as I say, I've just devised this first question, but what I'd like you to do is list the life cycle stages our sun will go through or has gone through. So could you list the life cycle stages that a star like our sun in this case, has gone through and will go through? 10th person just joined in. Oh no, they've gone again. I was going to repeat the question for them, but we seem to be sticking at 9. So that was question 1. Question 2, when the speed of an object is doubled, what will happen to the amount of kinetic energy stored in it? When the speed of an object is doubled, what will happen to the amount of kinetic energy stored in it? Question 2. Question 3, I'd like you to describe, but it does not need to be detailed. I'd like to describe the resistance temperature characteristic of a thermistor. Describe the resistance temperature characteristic of a thermistor for question 3. Now to question 4. What did John Dalton contribute to our understanding of atomic theory? What did John Dalton contribute to our understanding of atomic theory? Question 4. And question 5, a very short, simple one to finish with. What is the unit of mass? What is the unit of mass? I hope I gave you long enough on question 4, which is why I was just pausing a little longer after question 5. We'll go through those now. We'll see how you did. So in the first one, I wanted you to list the life cycle stages our sun has either gone through already or will go through in its lifetime. Well, I wanted to start at protostar. You may have even included nebula before that. That would be great. But from nebula, we go to protostar, and that's really where I'm starting the story. A protostar, once the force is balanced, once fusion switches on and it's balanced by gravity, a star reaches its main sequence. So we have protostar followed by main sequence. Essentially, when the hydrogen runs out, the star has ended its stable life cycle and it starts to fuse heavier elements. And when it does, it expands and it becomes, third part of the answer, a red giant. So we have protostar, then we have main sequence star, then we have red giant. Now, a star like our sun isn't very big in the grand scheme of things. And so it has, compared to some stars, a less spectacular ending. Once it's been through its red giant phase, it will become a white dwarf. And there I'm happy for the answer to enter. As long as your answer has protostar, main sequence, red giant, white dwarf, I'm absolutely fine. But you may well have added this idea that it then sort of cools down through the colour spectrum. So it goes from being a white dwarf through to something called a brown dwarf. And really its eventual death is something called a black dwarf. So you may have tacked those onto the end. So from white dwarf to brown dwarf, any colour of dwarf star really in between, ending at black dwarf. I hope that's clear enough. And that will be the life cycle of a star like our sun. Question 2 was, when the speed of an object is doubled, what will happen to the kinetic energy stored in it? The answer is it will quadruple. Well done if you got that. If you didn't, just remember the kinetic energy equation. Ek equals 1/2 mv squared. So the v bit, the speed, is squared. So if you double something and then that thing is squared, if you times 2 and square it, that's times it by 4. So yes, if you double the speed, you quadruple the kinetic energy because speed is squared within the equation. Describe the resistance temperature characteristic of a thermistor was question 3. Really, I was just looking for this. As resistance increases, as temperature increases, resistance decreases. As temperature increases, resistance decreases. Question 4, what did John Dalton contribute to our understanding of atomic theory? Well, I've always thought that he didn't really contribute, rather resurrected an idea. Basically, he brought us back to something that Democritus, an ancient Greek, had talked about thousands of years before, that all matter was made up of tiny pieces called atoms, atom being the Greek for no cut, the smallest thing you could cut something into. Well, John Dalton, about 200 years ago, simply resurrected the idea. It was at a time when we were more interested in the microscopic once again, because the microscope had been invented and we discovered cells. Robert Hooke had done that in the century before. So yeah, John Dalton resurrected the idea of the atom, that all matter was made of tiny particles. And as long as your answer gets that across in some way, it's correct. And then question 5, what is the unit of mass? Kilograms. Mass is measured in kilograms. 5 more questions coming up from more recent stuff. First, I'd like you to draw something. Could you draw the field between two like poles? Draw the magnetic field between two like poles. Question 2, another drawing one. Could you sketch the potential difference time graph produced by a dynamo? Could you sketch the potential difference time graph produced by a dynamo? Question 2. Question 3, could you give 3 ways of increasing the force produced by a motor? 3 ways of increasing the force produced by a motor. Question 4. What type of magnet loses its magnetism when it's removed from a magnetic field? What type of magnet loses its magnetism when it's removed from a magnetic field? And then question 5, what is an electromagnet? Just describe what you need to make an electromagnet. What is an electromagnet? Question 5. Right, we'll go through those ones. There's a couple I need to draw, which is why I was just looking for this pen. Starting with draw the magnetic field between two like poles. Well, coming up to the camera again, two like poles. So we don't tend to draw whole magnets in diagrams like this, but 2 poles. Here's a south, here's a north. Whoops, here's a south, here's a north. The magnetic field between, 2 like poles, not unlike poles. Apologies. 2 like poles, so in this case 2 souths. You might have done 2 norths. And then the field would look something like this. So that's the general shape. And then we just need to specify the direction correctly. Well, magnetic field lines always go from north to south. So in this case, arrows pointing to the south sides of these magnets. Clearly, if you went for 2 norths, then the arrows would just be going in the opposite direction to that, away from the poles that you've drawn. But that's the magnetic field between 2 like poles. Question 2 of this second section was the potential difference time graph produced by a dynamo. We had the one for an alternator in our last quiz, I think. Well, for a dynamo, first we'll draw the axes. We have positive voltage, negative voltage, 0 in the middle. A dynamo will only produce a potential difference and therefore a current in one direction. It does increase and decrease in a cycle, but it always stays moving in the same direction. That's the potential difference time graph for a dynamo. Question 3, give 3 ways of increasing the force on a motor. Well, again, I'm just going to divert my whiteboard just to remind you that the easiest way to think of it is to think of an equation, F equals Bill. I will add a fourth answer actually, but this gives us three answers. So to increase the force on a motor, you can increase the magnetic field strength, B. You can increase the current, I, or you can increase the length of wire in the field. And that's why I'm going to accept a second answer there, which is basically you could have said something about increasing the number of coils. That would have the effect of increasing the length of wire in the magnetic field. So that was question 3. Question 4, what type of magnet loses its magnetism when it's removed from a magnetic field? The answer is an induced magnet. And question 4, what is an electromagnet? Well, I was just looking for this idea that it's a solenoid, or you might have said a coil of wire, with a current flowing through it, but it's wound around an iron core. So a solenoid wound around an iron core would be a perfectly acceptable answer to that question. Just pausing, looking at my screen. There's no questions that have come up during that, I don't think. So we'll press on. Do give yourself a mark if you wish to, out of 2 lots of 5 or out of 10. But hopefully that was a good recap. And so we're going back to transformers today. My coffee table is bare, where I normally move my camera to when there's a demonstration. So that tells you that I've taught you nearly everything I can about this topic. We now need to just wrap some maths around our understanding of transformers. So yesterday we learned that transformers are these really clever devices that link 2 circuits magnetically. You wrap 2 circuits, 2 coils of wire, around an iron core, and whenever one circuit is alternating, that iron core feels a changing magnetic field. It creates a changing magnetic field. And so the second coil, the secondary coil, that experiences that changing magnetic field, and through the generator effect, an alternating current is created within it. And this becomes really useful when you either step up or step down the voltage. You have more turns on the secondary than the primary, and you can step up the voltage, or more turns on the primary than the secondary, and you can step down the voltage. And that allows you to manipulate how many volts are flowing through any given circuit. Well, we're going to do the maths around that now. So I'm going to tell you 2 new equations. We'll practice them, then it will be over to you. So I don't think you'll need pencil or ruler. I'm not planning on drawing much. I might sketch something out. I might sketch out a transformer coil. So if you don't want to do that freehand and you want rulers and pencils, just make sure you have a pencil and ruler at hand, but you should be fine with pen as well. And just bear with me a moment while I adjust my camera. Just going to make sure it's nicely focused as well, which I think it is. Right. Thank you for bearing with me there. So, 2 new equations. They are quite powerful equations. They allow you to learn a lot about transformers in different situations. They don't particularly have names, these equations, and our title was Transformer Equations. So I'm just going to put a subheading, Equation 1. I'm just going to seek out a ruler to underline that with. I think I'll use my trusty pencil as it's to hand. So equation 1 is really a set of ratios, and it's really useful if you know one set of things about one side of an equation. You can use it to find something else about the other side of an equation. And we'll write it out in its full wording first, I think. And so there's quite a lot to fit in, especially if I'm working in pen as I am doing in felt tip. So you're going to see me sort of stack how I write this a little bit. It might be a little bit messy, hopefully better in your book. I'm going to do some shortenings, and so I'm going to say PD instead of potential difference. PD across primary coil. And this is a ratio, this equation. So it's divided by PD across secondary coil. Equals, and this ratio is just an equality that turns out to be really useful. It's perfectly proportional and in ratio with the number of turns on each coil. So I'm going to shorten number to no like that. It's a standard shortening. Number of turns on primary coil divided by number of turns on secondary coil. And you can bet we like to shorten that because that is a pain to write again and again and again. So we use subscript to separate things out. So potential difference across primary coil becomes VP, P for primary. And potential difference on secondary coil becomes VS. And that equals, and we use capital N for number of turns. So capital N subscript P means number of turns on primary coil, divided by capital N subscript S, number of turns on secondary coil. Well, I'd like to just include one quick worked example, and you'll really quickly see how this would work. Depending on which one is the unknown, it can be a little bit more difficult to work with. But let's do this worked example. So I'm very much making this one off the top of my head. Let's do a worked example. And we're going to sketch a transformer core. Didn't underline that terribly effectively. So, yes, rather than writing a wordy question, we'll just draw out everything we know about a particular transformer. So transformers are always built around an iron core. So we'll draw an iron core. And let's say we know lots of things about the primary, but we don't know everything about the secondary. So let's say in this case that, and I'm going to make it a slightly more complicated one with a bit more rearranging to do. So let's say that we know that the voltage across the primary coil, we'll write an amount of volts, we'll say it's 230 volts. And that 230 volts is being supplied into the coil that's wrapping around this, like that. And let's say that the other thing we know, and this diagram isn't an accurate diagram because I'm going to tell you that on this primary coil, there are, let's choose a number at random, 500 turns. And let's say that on this one, there are many fewer turns than that. That there are 150 turns. And what we're being asked to find out is what the secondary voltage would be. So I'm just going to put a question mark there. Well, some of these, sometimes you can do by inspection and by eye. But with the numbers I've chosen numbers that I don't think are that easy to do in your head. What we do know, just by the setup, more turns here than here, is we know it's going to be a step-down transformer. So we'll know we're somewhere in the right direction towards an answer if this number ends up being less than this number. This should be working as a step-down transformer. But let's see, let's run the maths of this. So we employ this equation. And because it's the first time I've been through it, I'm going to state the equation first. So Vp over Vs equals Np over Ns. And I'm going to go on to a second piece of paper because I've just run out of space, but you can just carry on where you are. And then we simply put the numbers where we know them. So this is, and just by convention, this side's primary, this side's secondary. So we know that the potential difference on the primary is 230. So where Vp was, we put 230. Divided by Vs, that's our unknown. That's the thing we don't know. But we know everything about this side of the equation. We know that the number of turns on the primary was 500, divided by the number of turns on the secondary, which was 150. Plenty of options as to what you can do next with this. True to form, true to the way I've taught you all this time, I'm going to make this look as nice as possible. And so what I'm going to do first is simply work out what 500 divided by 150 is. I'm doing that on my calculator, and 500 divided by 150 actually isn't a particularly nice number. It's 3.3 recurring. So actually on this occasion, I'm going to keep it as a fraction. And I'm simply going to rearrange. Now, my guess is that amongst the people I'm talking to, you're mostly pretty good at rearranging things like this. And therefore, I'm going to do lots of steps in one. But I won't do every step in one, actually. I will take it one bit at a time so you can see exactly what I'm doing. My big problem here is that Vs is on the denominator. It's on the bottom of the equation. It's not a very good place to solve things from. So I need this to be on the top of the equation. And the best way to do that is to multiply both sides by Vs. I'm not going to show that detail. I'm just going to show the outcome. But what I need you to imagine is that I've multiplied both sides by Vs to get rid of this on the denominator. So we end up at this stage that 230 equals 500 divided by 150 Vs. I've multiplied both sides by Vs, and that's had the effect, after some cancelling, of leaving Vs up here. Well, again, I'm going to do some moving around all at once. I now want this over here, but I'm going to take it one bit at a time. So first I'm going to multiply both sides by 150, then I'm going to divide both sides by 500. But all I'm going to show you is the outcome of doing that. So if you're confused, watch this section back, because hopefully the words I'm saying now will describe what I did and why. So I'm multiplying both sides by 150 and then dividing both sides by 500. So you end up with 150 times 230, all divided by 500 over here. And that will equal our answer. That will equal the secondary voltage. So all I need to do now is put that into a calculator. So 150 times 230 divided by 500. And it turns out the secondary voltage that comes out, I don't know if you can see that on the screen, but it's 96 volts. So I'll just simply finish by saying, therefore, Vs equals 96 volts. Well, that's the first equation. I'm just going to show you the second equation, then I'm going to hand it over to you to do some examples of it and see how you manage. The second equation, I'm just going to grab a little more paper. I seem to have left myself short on paper today. Just bear with me one moment. Apologies for that, and I seem to be down to lined paper now. So a subheading, please, and the subheading equation 2. And this equation comes with an important term and condition. And it's this. Just write this before we write anything else. In this equation, we assume the transformer is 100% efficient. Now, what that means practically is that all the electrical energy in the primary gets through to the secondary. So if you have, I don't know, 300 joules of electrical energy in the primary circuit, then 300 joules will end up in the secondary. All of the energy is transferred efficiently. It's an important term and condition here. But the equation itself, again, we'll write it in full first. And it's this. Again, I'm going to shorten potential difference to PD. PD across, and just watch where I stack my words here. And I'm going to shorten, I'm going to write in full secondary. I'm going to drop the word coil now because I think we understand it from context. Multiplied by current across secondary equals PD across primary PD across primary multiplied by current across primary. Again, it's a pain to write out in full, so we shorten things, and it's the same subscript system as before. So potential difference across secondary becomes Vs, and current across secondary becomes Is. So Vi on one side equals Vi on the other side. Remember, and you don't need to write what I'm about to, but you may wish to, it's not part of the equation, but Vi, that is just power. We learned that when we studied electricity. So what it's really saying is however much power you have on one side is equal to however much power you have on the other side. That's all it's saying, and it goes back to that term and condition that we wrote at the top of the page. Because energy is transferred fully, it's the law of conservation of energy. If you have a certain amount of joules on one side and it's 100% efficient, then you'll have that same amount of joules, or in this case watts, on the other side. All the power will transfer perfectly. So you can see how this equation will work as well. If you know two things on one side and one thing on the other, you can work out the missing thing. And so we'll do one worked example, then I'll hand it over to you. So a subheading worked example. And again, it's just probably best that I draw it out, but there's other things to say this time. So yes, we have a coil. We have a core, sorry. And on this one, we're not going to talk about number of turns. That won't be important to us, but we will talk about currents. So I'm going to draw an ammeter in, and voltages. So I'm going to draw a voltmeter in. And you'll forgive me this slightly messy notation. I'm just being a bit obsessive now. I was about to draw a circuit that doesn't technically work, so I've had to put my voltmeter in parallel. That was not my original intention. But this circuit is feeding into a core again, a coil, and coming out there. And I'm going to assign some numbers to this in a minute. We're going to assume left is primary again over here. And again, the number of turns is not important here. That's not important for this equation, but I'll deliberately just make it one more on this side. That's not particularly significant. But what I will do is put in another ammeter and another voltmeter. And I don't know what component's being powered here, but let's just imagine it's a light bulb or something like that. And feeding into the transformer. So we have that sort of setup. Now I'm just going to put a few numbers in. Let's say in this case that the thing we don't know is the primary voltage. So we don't know what voltage went in, but we do know that a current of 0.15 amps is flowing there. And let's say on this side that there's a current of 0.10 amps, and that the voltage we're getting out is 12 volts. Well, let's employ the equation to work out that primary voltage that was being supplied to the circuit. So it doesn't really matter which way around we write this, but I'm going to keep it as before. VS equals VP IP. Oh, some people are questioning my final answer, are they, on the previous one? Sorry, I've just seen what's there. You're quite likely to be true that I've made a mistake. Did I just read it wrongly off my calculator? It's possible, I won't dwell on it too long, I'll finish this worked example. It's possible on that one that it was actually 69 and not 96, and I simply misread in haste. I don't think I've done anything mathematically wrong, though I'm just second guessing myself now. No, I don't think I have. But it's possible I just misread the calculator screen. So do correct your notes on that one if it turned out to be 69 and not 96. I possibly just misread things on my screen. Sorry, back to this one anyway. And so we know the secondary voltage is 12. We know the secondary current is 0.10. We know that the primary current is 0.15. What we don't know is the primary voltage, so we keep that as it is. This one I think a good deal easier to rearrange, nothing on a denominator to worry about here. So hopefully most of you will be happy if I skip to this step. 12 times by 0.10, all divided by 0.15. And I'll run that through a calculator. And again, please quibble and query if you think I'm wrong on any of this, but I get the answer 8 volts. So again, it's just another equation you can use to find out a different set of things about transformers. Well, let me just adjust my camera and then set you off on some work. Right, yeah, I hope I wasn't wrong on that first one. I hope I've cleared it up if I was. I will just check that while you're doing some work. But I got you to print out 2 questions. Didn't quite realise how many pages they cover, and it's just because they're full of diagrams. They're not particularly huge questions. I seem to remember there were 20 marks available in it, but as we've done quite standardly, I'm going to give you 15 minutes. And if that's too short a time, we'll see at the time. But I'm going to put 15 minutes on the clock. Let's see how you do on these questions. Best of luck. Thank you. Yeah, I can confirm I did misread that first one. So if you haven't already, alter your notes. The final answer, not 96, but 69. Just misread the screen. Thank you for picking up on that. Well, halfway through the time, my sense is, and I'm just reading through these questions fully, they're the hardest questions I've given you. So I'll give that warning with 2 minutes to go. If there's a substantial need for more time, I'll ask you just to let me know, because I think these are some really tough questions and you might need more time than the 15, but we'll see. This is my 2-minute call out. If you need substantially more time, just indicate there and I'll maybe put 5 minutes more on. If not, we'll go through this in 2 minutes time. Thank you. Right, that's time. I expect some of you might have been being a bit shy by not asking for more time, but that's absolutely fine. We'll go through it now. However far you got, and you can always fill in answers and look back over it to make sure you understand. So purple pen if you wish, but we'll just go through it. And I'll try and be as thorough, but also as sort of swift as I can with this. So I'm just adjusting the camera. And yes, we had something of a bumper crop of questions. It was only 2 questions, but many parts to them, many diagrams as well. So question 1 started. I'm just checking, no questions at this point. Scientists have used a satellite system to investigate the idea of generating electricity in space. As the system orbited the Earth, a 20-kilometer wire was reeled out. A 20-kilometer copper wire was reeled out. Before the wire snapped, a current of 1 amp was induced in the wire. Remarkable experiment, 20 kilometers, that is a heck of a lot of wire. I didn't know of this, but I assume it's something that really has happened. 1A said this: what provides the force needed to keep a satellite in orbit around Earth? Answer: gravity. Well done if you got it. Maybe a trickier question follows though. Explain how a current is induced in the wire. And I'm going to predict at this point, I think a lot of you will get to possibly not 3 out of 3. We will see. Well, lots of ways to express the first point to get across, but first you've got to have the idea that the wire cuts through Earth's magnetic field, which I'm just going to shorten to Earth's field. I think cuts through, we could replace that with moves through, but the idea that the wire moves through a magnetic field, you have to link it to this idea of the conductor moving in a magnetic field. You may drop in at this point some reference to the generator effect. I think that gets you the second mark. But we may wish actually to describe what the generator effect means. What it means is that a potential difference is induced. And it's perhaps this bit that I'll be really impressed if you got. Because right when we started talking about the generator effect, we had to sort of separate out the idea. First, you induce a potential difference. And then if the current is if the wire is part of a complete circuit, then you get current flow. And that's where we get the third mark, is for recognizing that the wire must be part of a complete circuit. So I'm going to put something like, assuming wire is in complete circuit, comma, this potential difference, PD, causes current flow. No way, of course, that you'll have expressed it in my words, but it's this idea that, yes, the generator effect causes a potential difference to be induced, but it's only when that wire is then part of a complete circuit that we have a current. And the question was about explain why a current was induced. And that's why that third step necessary, as I said I would expect. I think a lot of you might have got 2, but perhaps not 3. Well done if you did. The next part carries on. An alternator is connected to a data logger. The data logger is connected to a computer. Figure 2 shows how the output potential difference of the alternator varies with time. And question C goes like this. The coil inside the alternator now rotates at twice the frequency. Draw on figure 2 to show how the output potential difference varies with time at this new frequency. So this is figure 2, we're drawing on this. There's actually 2 changes to get across. If it spins twice as fast, well, clearly we're going to have a higher frequency. We're going to have more full wave cycles within the space, but you also get a higher output potential difference. So I'm going to mark on every peak here. So the peak happens sort of twice as quickly, as it were, but it's also twice as high. So our wave is going to go through that point. It's going to pass 0 there. It's going to reach a peak, or a trough in this case here, and it's going to carry on in this sort of pattern. And just taking my time to make sure I pass through all the correct points. I'm doing this slightly at speed. Once I draw it in, you'll see much more clearly, but really well done if you got these ideas across correctly. And the idea is that our new trace should look something like this. So There were 2 changes to get across, and so you get a mark for each. Let's say you only got that they'll be twice as frequent. There's 4 full waves on here as opposed to the 2 that there were before. Well, that gets 1 mark. But the second mark is for recognizing that if it spins twice as fast, you have twice as much voltage induced at its peak. So the peak goes twice as high as before. That's the second mark. Again, a really subtle question, and so really well done if you got that. And the question continues. Another type of generator is now connected to the data logger and computer. Figure 3 shows how the output potential difference varies with time for this generator. And now we have it. And what name is given to the second type of generator? Well, it was looking for the answer dynamo there. Well done if you got it. And then it says look at figure 2 and figure 3 and give one difference between the outputs for these two types of generator. Well, I think the obvious one is that this is always in one direction. So the potential difference induced is always in one direction. It stays above 0. That's certainly the answer I'm going for. The induced PD in dynamo is always in one direction. And then just to be absolutely clear, even though it's only worth 1 mark, I'll put in the alternator, direction varies. That's certainly how I'd answer that question. Next question. We're nearly at the end of question 1. It was our first chance to try one of our calculations. The charger used to charge the battery inside a laptop computer contains a small transformer. The charger plugs into the mains electricity supply. The mains electricity supply is 230 volts. The number of turns on the primary coil of the transformer is 690. The number of turns on the secondary coil is 57, and we're being asked to calculate the potential difference applied by the charger across the battery inside the computer. I think it's always a good idea with these questions to assign symbols as we go. So the mains is supplying, the main is the primary one, the first one in this sense. So 230 is going to be our VP. Then we have 690, that's going to be our NP. Then we have number of turns on the secondary coil, that is NS. And we're being asked to find VS. So if it were me, and you don't have to do it like this, but I would do that, and then I'd lay it out. Now, there was one little hack I didn't really tell you about with this equation that's quite useful. And I'm just going to write it underneath first, that if you have VP over VS equals NP over NS, well, VS is on the denominator, and we solved it that way before. But of course, this equation is equally valid if we just flip that right away. So I'm not going to start from this equation. I'm going to start with the equation flipped up. So I'm going to go straight to VS over VP equals NS over NP. It's the same equation flipped up, and it works. It's equally valid, and it just means less rearranging to do. So now I can put the numbers in where I know them. Well, I don't know VS. I'm trying to find VS, but VS divided by 230 equals NS, which was 57, divided by 690. And therefore, to find VS, and sorry about the slight mess when I'm doing this in felt tip, you would have that it's 57 divided by 690 times by 230. And you just run that through a calculator. So I'll do that now. 57 divided by 690 times by 230. And again, you can tell me if I'm wrong, but I'm pretty sure the answer there is 19 volts. That certainly looks plausible to me. 19 volts. So that question was out of 3 and the whole thing out of 11. You can give yourself a mark out of 11 if you wish. But I'm going to go on to question 2 now. A student used a simple transformer to investigate how the number of turns on the secondary coil affects the potential difference across the secondary coil. The student kept the potential difference across the primary coil fixed at 2 volts. Now, I don't know if we're going to need this yet, but I am just going to put VP right next to that before I get confused. And it's fixed, it's unchanging in this particular experiment. Figure 1 shows the results collected by the student. And so, yeah, they've made 5 different readings there, and they've been plotted. There is an anomalous point, and that's what question A is about. Question A says, figure 1 contains 1 anomalous point. Suggests 1 possible reason why this anomalous result occurred. Well, I'm going to tell you the mark scheme's results here, the mark scheme's ideas here. They've gone for 2 central ones, either that there were too few turns. In other words, when he was winding extra turns around that coil, he sort of miscounted the number of turns or coils on that secondary coil. Or, and I wouldn't have gone for this if it were me, but an acceptable answer seems to be PD across primary reduced. So just for that result, the 2 volts wasn't actually true, is what it's suggesting there. Just for that one result, it was less than 2 volts being supplied. That seems very unlikely to me. That's not the kind of thing I'd go for. I'd go for the one that's more in control of the human doing the experiment, which is the too few turns across the secondary coil. But I think a tough question there. You may have had other answers, and you can use your judgment if you think they are sort of plausible there. Question B. The transformer changes from being a step down to a step up transformer. How can you tell from figure 1 that this happens? Well, for that you needed to recognize what the question told you. And it's this little mark I made here. The question told us that the potential difference of the primary was fixed at 2 volts. And you can quite clearly see the potential difference of the secondaries here. So here's our 2 volt mark. And you can see actually it goes above that. So the basic answer here, and I'll write it in a moment, is basically because the potential difference across the secondary goes above 2 volts. The primary is kept to 2. So if it managed to go above it, it must have been at some point, at that point, it must have become a step-up transformer. So how can you tell from figure 1 that this happens? And I'm doing this in note form, but because Vs, the voltage on the secondary, goes above 2 volts, 2.0 volts. Well done if you got that, or something to that effect. Now the question continues. A spot welder is a device that uses a transformer to produce a large current to join sheets of metal together. Figure 2 shows how shows a transformer demonstrating how a large current can heat and join 2 nails together. So yeah, the ends of the nails melt, they get welded together, and so those 2 nails become 1 piece of metal. We've got various things labelled. No harm always in just making the notes next to them. So there is an NP there. There's an S there. There is a power. Now I'm going to leave that unlabeled, except I might put a P next to it just to remind myself actually. And there's the potential difference across the secondary coil, so there's a VS there. We'll keep all that in mind for what might come up. But on question C it says, how does the amount of infrared radiation emitted by the nails change when the power supply is switched on? Well, this is really just testing, do you know what infrared radiation is? And it's intrinsically linked to heat. It is how heat travels. It travels as infrared waves. So it increases is enough here. The nail gets hotter when it's switched on. That shows that the infrared increases. Well done if you got it. And then we come to question D. And it says, and it's worth 5 marks. A little bit of thinking required here. Calculate the current from the power supply needed to provide a power output of 336 watts. So the current from the power supply, the primary current it's after. That's certainly how I read the question. It's after IP, the current from the power supply. Use the data in figure 2. And we can assume that the transformer is 100% efficient. In other words, it's telling us our equations will work here. It's fine, we can make that assumption. So let's collect what we know, and it's actually a little bit of a mess of what we know. The equation we'd like to use was this, VS IS equals VP IP. But we don't know everything we need to know to be able to do that. We're being asked, just to remind you in the question, we're being asked to calculate IP. We're being asked for that. And we have the secondary current. No, we don't yet. But we do have the secondary power. And we have the secondary voltage. So we have that. We don't directly have that. We don't have that as I'm reading it. And so there's a lot of unknowns here. There's a lot we don't know. We can't get straight to this. We have to be more clever about this. What we do know is we have a power. So remembering that, I'm going to turn back over. P equals VI. What we do know is that we can find this. And I'm going to do that first. There's lots of orders you could take this, but I'm going to work out the secondary current first, and then use that to find out. Oh, I'm pausing because I think there's another way to do this. I'm going to go for the transformer equation first. In fact, I think that's all we need to do. Yeah, we're going to use the transformer equation, then use the power equation. So, apologies, I just think this is going to be a better way of doing it. So VP over VS equals NP over NS. I'm going to work from that equation first. We'll put in the values where we know them. We don't know a primary voltage, but we will find it. We do know a number of turns, NP, 640. So if I'm rewriting this, 640 goes there. We don't know VP. We do, however, know VS. VS was 1.75. And the number of turns on the secondary was 4. Much more sensible to go to this one because we know far more about it. So I'm going to do the working for this down here, and sorry about the slightly messy layout, but you end up with that VP equals 640 divided by 4 times by 1.75. Run that through the calculator. And when you do so, it comes out as 280. You can shout up electronically if I've made any mistake there, but 280 volts I think is right for that one. So let's look at where that now leaves us. So we now know the primary voltage was 280. Well, that will allow us to work out the primary current, but it takes a leap of understanding. So we're going to focus everything over here now. So we now know that VP equals 280. And again, it appears we don't know enough to work out what we wish to, but we do because we know the transformer is 100% efficient. We know the power over this side was 336. Well, that little clue about the efficiency tells us the power over this side is 336 watts. So this question is testing, do you recognize the implication of that 100% efficient thing? The 100% efficient thing is telling us whatever power we have over here, we had over here as well. And so now we know these two, we can work out that input current, that primary current. So I'll go back to my space for working out. And it's a slightly different use of that second equation I told you, but we're going to go to P equals VI. And in this case, it's all about the primary side. We're not worrying about the secondary side. 336 goes there. And that equals the potential difference, which was 280, times by a current. And that current is going to be our answer. So I equals 336 divided by 280. We run that through a calculator. And it comes out as 1.2. 1.2 amps. So our primary current, and a slightly messy way of bringing it about here, is 1.2 amps. Well done if you got that, especially, and well done especially if you got it within the time. I'm just going to turn this back and say some goodbyes. Sorry that took a little bit longer to go through, quite involved questions. We've been about 15 minutes longer than the normal lesson. But I think my thank yous need to be more broad than that, because actually that brings to an end the physics that I need to teach you. Finally, the course is finished. So we've done last year energy, electricity, particle model of matter and atomic structure. And finally this year we've done forces, we've done waves, we've done magnetism and electromagnetism, and we've done space physics. So that is GCSE physics complete. And thank you for sticking with me, you 10, right to the end. It really does mean a lot. So this may well be our last lesson. I'm absolutely open to the idea if you want to round things off with some sort of quiz next week. But nor do I want you to carry on coming and tuning into these out of any sense of duty. I only offer that up because it's just a particular time at the moment where there's perhaps not very much to do, and it's a nice change to your routine. So if you fancy a quiz next week, do indicate by giving me some emails. But failing that, that is us done. So thank you so much, not just for tuning in now, but for all your work over the past 2 years. You're absolutely wonderful, standout people. And I imagine amongst these 10, there's a lot of you considering at least doing A-level physics, and you would absolutely fly with it. And it will be physics' gain if you guys did. So, last thing I need to say, if any of you need any help with anything, you never, not my pupils, I'll always look out for you. You know exactly where to find me. You know exactly how to get hold of me. So if it's for references, for advice about whether to take A-level physics, or even advice about dropping it, if after a few weeks you think, oh, this is not what I thought it was going to be, you won't disappoint me if you want to get in touch and discuss dropping it. I'll be good at checking my emails and good at getting back. I'll try and hold myself to that. So, thank you very much. Take good care. If you want to do something next week, absolutely open to it. But I will say thank you and goodbye for now. And stay safe for as long as we need to stay safe. Bye for now.